Here's introduction to calculating determinants beyond 2x2. We haven't talked about that yet. We know that determinants have to do with whether a matrix has an inverse, and therefore it has to do with solving an equation with A, the matrix that we're calculating the determinant of, as its coefficient matrix. We looked at how these are integers, the determinant gives us an idea of how complicated the answer might be, the denominators that we might get for the fractions. We looked at 2x2 determinants and talked about how they calculate area of a parallelogram. But 3x3 determinants, and we know how to calculate the actual value of a 2x2, but we don't know how to do a 3x3. Now, I don't want to derive, it's much more than we want to do to derive why what I'm going to give you is the right formula for the determinant. That's a great thing to do in a linear algebra class, but I'm going to show you how it's usually calculated, at least for 3x3 and often for 4x4. There's more different methods that are more efficient for bigger matrices. So what we do, I want to get some terminology here. This is exactly the same terminology in the book. The minors, those are, what we're going to do is we're going to calculate the 3x3 determinant by actually breaking it up into some 2x2 determinants. So the minors, let's say the minor, the 1, 1 minor, there's a bunch of different minors you can get. That's equal to the determinant of the 2x2 matrix obtained by deleting the first row, that's the one here, whoops, the first row and first column. And so that's going to be M11 is going to be the determinant. It's nice I can do this very easily with the computer. Delete the first row and what's left of the first column. That gives me a 2x2 matrix. So you're blacking out this row and this column, and you end up with this 2x2 matrix. And you take the determinant of that. Okay? So that, and we know how to do that. That's diagonal, the diagonal product minus the anti-diagonal product, AD minus BC. And so that's going to be minus 8 minus 45 is minus 53. Okay, I picked this randomly. It's not going to be a super nice number, so it's not going to be too bad. Okay, so that's what's called a minor. And it's minor because it's like a smaller determinant than what you set out to calculate originally. Another example would be, you might think, what does this have to do with a big determinant? We'll see in a minute. M23, for example, would be, that's the 2, 3 minor. It means focus on the second row. It's always row, column. Second row, third column. That's this entry 5. And we're going to delete its row and its column. And so we're going to delete the second row and delete the third column. And that minor is going to be 27 plus, because it's these two guys, minus a minus 16. So 27 plus 16, again, a fairly large number, 43. Okay. So, what do those have to do with anything? Well, it turns out that just calculating 3 of those guys and matching them up with a little more information is going to be a way to calculate the 3x3 determinant. But there's one other thing we need to do, which I like to call the secret minus signs. It turns out that it's not actually the minors that we really need. It's what's called the cofactors. I know there's a lot of terminology, but terminology at this point is not crucial. So, like A23, these are called the A's. A23 is the 2,3 cofactor. It's just going to be plus or minus I'm not going to write it in the standard way because I want to emphasize that it's definitely a known sign. We're going to fill that in a second. Times M23, times this guy. And so what we're going to do is we're going to put in a sign, and the sign pattern is very easy to remember. The way the book says it is it takes, I'll write the way the book says it, and then I'll say how people most usually do it. They say take I plus j, that's 2 and 3. This is going to be I, and that's going to be 3. So you take the row and the column, you just add those two numbers, and you take minus 1 to that power. And so that's going to be minus 1 to the 5, that's minus. So we're actually going to get minus this determinant, which is minus 43. And that's called a cofactor. And here's how people usually remember this. Well, I don't know. Yeah, I think people usually remember this way, I'd say. People I know. It's to take the 3x3 matrix originally and just put a checkerboard pattern of pluses and minuses. So I like to call this the secret plus or minus signs that you have to remember. It's just a checkerboard pattern. Okay, so this pattern of signs says if we're going to calculate these 2x2 determinants, this is how we make them into cofactors. Now, how do we use the cofactors? Okay, so let me just bring down the actual matrix again and show you the whole calculation. I wanted to give you that terminology so I could say minor and cofactor and stuff like that. But the main thing is the calculation. What we do is we expand. It's called expanding around a single row or column. I'm going to expand around the first row because that's often a standard way to do things. What we do is we just go at all the entries in that row in turn, and we just write down the entry in the row, and then we just multiply that by the cofactor that corresponds to that entry. So it's going to be 3, which is the 1, 1 entry, times A11, plus 4 times A12, because that's still first row, second column, plus 7 times A13. Okay, and you don't have to write that out in this way. It's just nice to have this terminology. What usually people do is they just leap directly to the definition of the cofactor. So it's this entry, and then you just picture blanking those row and column out, and then so times that, and I'm going to do that minor, with a plus sign because the cofactor is the same as the minor here. I know this is all very weird and strange, and this is the part where it would take a long time to really justify why on earth we do this. There's a lot of theorems, deep theorems involved here. Now we're going to take 4 times the cofactor. I usually take the minus sign though out, and then we're going to take the determinant of another submatrix. So now we're going to blank out first row again and the middle column. So this is taking this matrix, blank out the first row, blank out the second column. We're only left with these guys. These aren't even really connected to each other in the original matrix, but they can kind of collapse together to make a 2x2 matrix. So this is the minor. With the minus sign, it's the cofactor, and then paired with 4. That's why it's called a cofactor. Factor, just means something multiplied. It's called a cofactor because it pairs with the 4 to make a contribution to the 3x3 determinant. Then we're back to plus because the determinant involved, the A13, is the same as the minor because there's no secret minus sign there in the checkerboard pattern. And we blank out that column or that row and that column. So it's all these entries with the secret minus sign in the middle paired up with these 2x2 determinants. This 2x2, the weird 2x2, which is these 2 and these 2, which gives this guy when we blanked out the middle column, and this one, these 2x2 when you blank out the last column. So these numbers don't appear in these determinants at all, ever. They appear in front of them. Oh, and I forgot the 7. Okay. So it's the 3, 4, and the 7 paired up with the appropriate minors, and then to make them into honest-to-God cofactors, this minus sign is crucial. Okay. And so that, you calculate it out, all those determinants, it turns out to be minus 205. I know I cheated. I did it with a computer. But we know how to calculate those 2x2 determinants. Now, an interesting thing is that we could expand around any row or even any column. We could calculate this as we could do the middle column if we wanted to. So let's do that. 4 times, well, we know what the cofactor is there. Okay, we know it's got a minus sign. That's what the secret minus sign still resides there. It's exactly this contribution again. But then minus 1, okay, because the number's minus 1 here, times the determinant. Now we got to blank out, we got to take the original matrix, blank out the middle column, because I'm looking at the minus 1, and the middle row. So it's all the corners, it's the 4 corners. It's kind of funky. All these 4 corners survive and everything else gets blanked out. Now let's see, was it minus 1? The minus here is because it's actually a minus 1 entry. Do we need a secret minus sign? Remember the checkerboard pattern? No, there's a plus there. All along the main diagonal, it's always going to be plus. Okay. And then plus 9, that's the last entry in this column that I'm expanding around. Let me put a little note here. Here is expanding instead around the middle column, whereas this was the first row that we used here, and they all work. It's a lot of magical stuff about determinants. So here I'm going to copy in the matrix one more time. I'm going to delete that middle column and the bottom row. Okay, so it's 3 2x2 determinants. We know how to calculate those, AD minus BC, and let's check. Didn't press control. Let's try that again. Oh, that's annoying. What did I do wrong? You see, oh, that's good. I meant to do that, really. I wasn't careful about the cofactor. Minus plus minus. Minus plus minus. The checkerboard pattern is now minus plus minus. So this was a minus. I put that one in correctly. This one was minus because it was already a minus entry. That should have been a negative. And let's check it. There we go. Okay, so that does, the theorem is saved. Okay, it really is supposed to give the same answer. Okay, so that's a real brief introduction to calculating 3x3 determinants. And we'll do some 4x4 with the same method as well, but and we'll see that it's a pretty similar thing, but it gets really calculation intensive. But we want to do maybe one example. But that's the 3x3 case.